Hello everyone, I'm Cinay and welcome to this week's Technotalk. Here we discuss STEM-related topics with special guests to inform people and give them our perspective on modern concepts. Without further ado, let's greet our special guest of the week. Hello, Dr. Amanda.
Hi, how are you?
I'm fine, how are you?
I'm good.
So first off, you can tell us a bit about yourself.
Yeah. I am originally from Liberia and I grew up in Florida in the Midwest. I graduated from Purdue with bachelor's in materials engineering. And then I actually started my grad school program at the University of Akron in polymer engineering, but then switched halfway through. My advisor moved, so our group moved with him to the University of Colorado Boulder in the chemical and biological engineering department. And so that's what I have my doctorate in. And my research was I wanted to challenge myself. And so I went into computational material science, which was something that I had never dabbled with. You know, in undergrad, I pursued more the chemistry and definitely not the computer science programming route. So I felt like that was a side of me that I could try to work on and improve so that I could be a more well-rounded engineer.
Yeah, that's awesome. Like multidisciplinary work in every field. I think that's like so ideal. So yeah. So let's discuss today's topic, new advances in biotechnology and biological engineering. So in the recent years, biofields have received immense popularity. 2020, a Nobel Prize Award chemistry genome editing tool CRISPR-Cas9 to other examples of carbon nanotubes, wearable biosensors to healthcare systems creates like this variety of advanced solutions for biotechnological applications. Bioengineers are rapidly engaging in cutting-edge research, restructuring the way we live in this world. Thus, it isn't just like this methodology, it's kind of like the scientific, let's say, mentality that is forming. So, yeah. So to start with, as a materials engineer, interested in health and environmental issues, also having a PhD in it, chemical biological engineering, what are the benefits of multidisciplinary research?
I mean, so as engineers, we don't solve problems in a vacuum, right? It can be nice sometimes to simplify a problem in a vacuum, but for the most part, most challenges have a lot of complexities and nuances that involves several different aspects. So just by the nature of the research that we tend to do, the nature of the problems that we try to solve are multidisciplinary. So to tackle those problems, you need to come from a multidisciplinary approach. Case in point, the research that I did, that I worked on throughout my thesis was, something as simple as just, I worked on several projects, but I was looking at the interactions of polymers on carbon nanotubes, the interactions of some metal ions and hydroxyapatite. I'm looking at these material processes, these chemical processes, right? But then there's also the biological aspect that's involved with it. And then there's also the computational side of things, understanding programming, which then requires you to really understand physics, like quantum physics, mechanical dynamics, and so then I was like a part programmer. I had to learn how to be a programmer. So not only I could automate a lot of my experiments, but also understand the algorithm behind the computational experiments. Then, understanding a lot more of the physics that I didn't realize that there was a lot more physics involved with that. And then, the chemistry, the chemical reactions the interfacial interactions, absorption, desorption, and then the material properties that you're looking at. And sometimes that may even be the resulting mechanical strength. So there's like a whole slew of things that just from that one problem. And that's even carried over now to the work that I do. I work with the US Patent and Trademark Office as a patent examiner. And the art unit that I work in is it's the materials unit, but specifically the group that the topic that I work on is fertilizers. Mm-hmm. So I look at a lot of companies that are patenting new fertilizer compositions. There's a lot of organic chemistry involved, but then, understanding how fertilization works. You have these chemical processes. Let's say you're applying some nutrient package to the soil for the plants to uptake and grow and crops. You produce good crops, you can increase the food agricultural market, so forth and so on. So you have to understand the chemical processes that are occurring, right? Because plants don't just take in what you give them. They have to break it down and convert it into something that can actually be transported through their roots. Then you have the physical transportation, physiological, phenomena going on over there. You have the environmental aspects to think about. Something that is nutritious for the plants, but in excess can be like via runoff water and such, can pollute the water. So then it can become a toxic a chemical in that aspect, something that's supposed to be beneficial. You have sometimes the electrical components to think about it, because a lot of times you have to monitor the uptake and the growth. And so, depending on your part of the process, you also may need to work with like a team that's also working on the sensing technology to go along with the fertilizing technology. So it's, every problem that we solve for the most part, whether it's you personally that you need to build these different skill sets, or you need to reach out to an outside expert who specifically definitely you do. Everything that we solve as engineers has a multidisciplinary aspect. So multidisciplinary research is, it's in the nature of the game.
Yeah, like very logical. Like, so these like technically multidisciplinary research kind of enhances the vision of engineers to think as like problem solvers and think a variety of creative ways to solve a problem and to look at it from different aspects. So like it requires to make like let's say insights on other types of research. So it's amazing. And like these types of collaborations contribute to a, let's say, productive and fruitful research in the end. So yeah, right?
Absolutely, absolutely. And what you said about being creative, I think that goes hand in hand with multidisciplinary research, because you need to have experience in other areas to draw inspiration from.
Definitely.
It's not just what you're doing. And again, like I said before, I think sometimes it can get a little overwhelming to feel like, well, okay, I'm just a material scientist, but now I also have to be a physicist and also a programmer. And while it's important to sort of at least know what all these different aspects are that you need, it doesn't always have to be on just you, right? We always work in teams. Even our homework in college, I swear, I feel like it was designed to only be solved in groups. Like it was impossible to solve your homework by yourself,
Yeah, like teamwork brings dream work sometimes, and it's like, yeah, it's definitely a must in occasions. So I get it. So also, what are the new trends in biological engineering?
So when you were talking earlier about biosensors and carbon nanotube technology, both in the medical and I'm not sure if you mentioned this, but also in like the defense military aspect of things, especially more so in the biological field, biological processes, the ones that really drive the phenomena that we need, that we manipulate to optimize and improve, technology. It's really happening on like this nanoscale level, this atomic level. And it's in such a fast and short amount of time that a lot of the equipment that we use to try to observe these behaviors so we can manipulate them, it becomes challenging. And so I think one of the trends that have been around for sure in the last decade, but maybe now is becoming more progressive, is nanotechnology. Nanotechnology, not just using nanomaterials, but developing or fine-tuning the tools so we can actually observe things happening on a nanoscale level within a few nanoscales, a few nanoseconds, these reactions are like that, or even on the electronic level, electronic configurations, which impact molecular interactions, which impact the macromolecular, properties that we observe. So I strongly feel like the trend in the biological community is gearing towards combining what we do experimentally and with the measuring tools to help us observe what's happening on the nanoscale. And something that I noticed was, in the past few years when it came to publishing, a lot of the work was experimentalists were all looking to pair up with computationalists so that they could have these atomic scale resolution imagery to back up what they're observing. So now, like almost any paper that's worth its penny or whatever the phrase goes, you almost need to have some sort of computational collaboration. And then obviously likewise as computational students, I have the experimental component. So I feel like a very nice merge between the two can definitely help us to see what's happening on the atomic level. And that's where we're going, because those are the interactions that are driving that are the heart of the biological processes.
So yeah, great explanation, by the way. Love the touch of computational and biological together. Amazing. So I see that like we will learn and discover new and further challenges in every area and discipline in this like whole, let's say, gathering in the near future. So hope to see more discoveries and let's say in micro and macro like levels, and it's so with the whole nano technology. So yeah. Okay. Well, from your recent publications, I saw that you're working on polymer carbon nanotubes. So what kind of structural applications can be done with these, let's say, tools?
So carbon nanotubes are really, really cool materials. They're just rolled up graphene sheets. But the thing is, due to their very high aspect ratio, you can pack a lot in a very small amount of space. So you have, high mechanical strength, excellent conductivity, good electrical properties, good thermal properties, good physical properties. But as a material by itself, it can be a bit challenging to manufacture sometimes. So you have to create these composites with polymers, epoxies that are more flexible, can help space out the nanotubes, because really the property of the nanotubes are best enhanced when they're individualized, but they tend to conglomerate to bundle up. So the work that I did was about basically creating a matrix for the polymers to align in and be separated so that you can really maximize their properties. So structurally, it can be very applicable in areas of aerospace. Carbon fiber composites are just a really, really excellent replacement for other aluminum steel alloys or whatever materials that are usually used in airplanes, because they're stronger, but also extremely light. And so that is already such a huge plus. But then you get sometimes from the electrical properties, you can get things like electromagnetic interference shielding, and such, which is actually, I believe the research that I did was part of the application was you could use that on the nozzle of the plane to help during like thunderstorms, to keep an interference from like the radio's communications inside the plane. But aside from that, structurally, carbon nanotube composites are just, they're useful for more than just a structural material, because they have so many different, they have a variety of really good properties that people like. And so, like you said, you see them in clothes, and they're actually in like sportswear. I actually have a wallet that has like, it's like a graphene.
Wow.
It's like weaved. It's like a graphene weave on the surface of the wallet, because it's very good for RFID shielding, to prevent people from stealing information and such. So it's such a great material. So it has so many different applications aside from just structural. But structurally, aerospace is, I think, where it's being used a lot right now. Oh, and also vehicles as well. Yeah.
So true. Well, very interesting, by the way. Like, listen to you in very like interesting topics, and I just want to get into a lab and trying to, let's say, analyze them. So like these researches will bring like novel technologies, and it's starting to bring them like with wearable devices and on your own body that like kind of creates energy. So these types of whole systems with like CNT links and its great properties, it's just like a whole new world to kind of explore in. So yeah.
It feels like all of those fantasy novels and sci-fi movies are finally coming true.
Yeah. Okay. Well, let's say talk about students who are kind of aiming to get into the field, what skills do you think students should gain in order to pursue a career in engineering fields?
So from my own experiences, I think the things that you don't hear about as much, that they don't teach you, obviously you're going to get the skills that you need for your specific specializations, but some of the nuances of being an engineer or in the engineering field, having a career in engineering it kind of goes back to what you were talking about with multidisciplinary research.
Mm-hmm.
You kind of have to have you need to have your finger on the pulse a little bit on a lot of different areas. It doesn't mean that you need to be an expert in everything for sure, but know what's happening in other fields that are closely related. Know what's happening, as a materials engineer, I want to know what's happening biologically, environmentally, even the computer science world, because, I might need to pull in resources from that at some point in my work in solving problems. Case in point, I have with fertilizers, but sometimes the materials I use in fertilizers are also the same minerals I use with cement.
Oh.
And I was looking at this application, and I just, my job is to figure out the novelty. What really are they doing new? And they don't make it easy for you to figure that out, which, I get it. They need to get as much rights as possible. But, I Googled the processes, I Googled the materials. I understood on paper what was happening, but I felt like there was some nuance to the field that I just couldn't get because that wasn't my area. And so I called up a good friend of mine who's a cement chemist, and he helped me. And he was like, oh, well, generally, this is how we feel in that field. This is, why we think this process normally doesn't really work. And this is why people don't really do this. And then that, turned on the light bulb in my head. And I was like, oh, I never realized that when I look back at the application, I realized it was really theory that they were talking about. They hadn't actually said that they did it. And then that gave me like a different strategy. So there's nuances with each field that you don't get unless you're in that field. And so for engineering students, as you go into your individual areas, keep in touch with all of your friends who are in other areas. Keep your finger on the pulse and what's happening in the news with new technologies. It'll help you to sort of define your boundaries of what you know, and then that way you can know what you don't know. So then you have these connections that help you
definitely
blanks all around, because it's like we were saying before, you can't solve problems in a vacuum, and inspiration comes from so many different places. So it's something that it's such a intangible concept that it doesn't feel very scientific, very logical necessarily to even consider, but it's really important, I think, in making yourself a well-rounded, highly valuable engineer. You're not just a chemist, you're not just a mechanical engineer, you're this person who can very easily bring together all the other information that you'll need to work on that project, to move it to the next step forward, And when you create that versatility of resources for yourself, you become a lot more valuable to your company. Because you're not just one person now, you may be filling the roles of 2-3 different people. And,
So yeah. Nice observations. I consider that these skills and let's say the things that you talked about with the whole network, forming a network, having connections with other disciplined engineers, these are advices that can surely bring a beneficial outcome for students who are aiming by engineering and any types of field in this whole world of, let's say, discovery. So yeah, thank you for the tips for us.
And it's not, I give this tip because you already have so much work to do as engineering students. This isn't something that is like a whole new skill you need to go develop. It's something that you can very easily incorporate even now in your life. So hopefully that's something that can help you without adding more stress.
Yeah, thank you. Okay, well, that was an inspiring discussion. Thank you again so much to Dr. Amanda for joining us this week. Dear viewers, don't forget to keep up with our posts and additional events on our page Technotalks and YouTube channel. And if you haven't watched last week's video, please go check it out. See you next week with another interesting tech topic. Bye. Thank you for coming.
Thank you for having me.